Yeah, thanks for having me. So as Carsten pointed out, hello. As Carsten pointed out, we have been trying to explore some of these new methods and the new softwares and hardware in Copenhagen, and to see what we can use for them for physical oceanography or to understand climate. And I'll report on some of the successes we had. We tried a lot of things, not many of them work, but one thing that works quite well is Bayesian optimization of climate models. I'll give some examples here. Then we built a fully coupled model now in JAX. So I'll introduce this model here. And so this is basically an optimization of the standard climate models that we have today. But then there are also, for deep time applications, we will never be able to run a full climate model to the deep time. So then we have a second project where we try to look at emulators. We try to build emulators of climate system and then try to use them to understand deep time problems. So this is a two-part talk. Let's start with our Bayesian optimization tool, BEROPT. We all know there are like dozens of parameters in our climate models that we cannot fully quantify. And one goal of climate modeling is to optimize them, to have a nice, realistic simulation. And what people have been doing recently quite often is called PPE, perturbed parameter ensemble, where we just see what the spread of the solutions can be, assuming there's a spread of possible parameter ranges. And we take this one step further. So we start with a perturbed parameter ensemble. And based on this is the brain behind the operation, we build a surrogate model that creates an assumed loss function. And based on this assumed loss function, we have an acquisition function that picks the new parameter settings. And then we use these new parameter settings to start a new set of integrations. This works now. I mean, the idea of Bayesian optimization is an old idea. This works now quite well because we have these massive GPU resources on Lumi, for example. So we use here this on a 1-degree ocean model, and we could use the Lumi GPUs. So we use 32 simulations in parallel, and within 2 days, we have 70 years of integration. And then we can process the results, which mainly means we create the objective function or the loss function. In this particular problem, we look at the mixed layer depth. We want to optimize the mixed layer depth, which is a critical issue in many ocean models. And to make sure we don't deteriorate the rest of the solution, we also add the AMOC strength and the ACC strength and the 18-degree centigrade isotherm into our loss function. Then we have new objective function values, and then we build a new surrogate model, or we update the surrogate model, which has now many more points. And then we go do the whole loop again.
AMOC, you mean AMOC at 26 knots, or what do you mean?
Yes, 26 knots. So this is what I showed you last year as well, just to give you an introduction how this works. We use 9 parameters. Here's a list of the parameters that we choose. So there are several parameters tied to the TKE mixing scheme. And there are several parameters tied to Carsten's or the Eden and Craigbatch, Jenny McWilliams parameterizations. And then we also assume some uncertainty with the freshwater fluxes and the wind stresses. We see here the default values, and here the optimized values, where we have a better simulation. We're just looking at the zonally averaged mixed layer depth. The dotted line were the default values. So this is 60 degrees south, the equator, 50 degrees north. And we see the mixed layer is much too deep in the Southern Ocean. It's a common problem. And with our improved values, we have a much shallower mixed layer depth. And we also have a deeper mixed layer in the tropics. So we achieved with this new parameter optimization to deepen the mixed layer in the tropics and to make it shallower in the subtropics, which improves it in both regions. And one interesting insight here was that much of this has been achieved by reducing the zonal wind stress in the Southern Ocean, or you reduce it everywhere. and we can look at the differences between EIA5 winds and the scatterometer winds, and indeed EIA5 winds, which are used to force this model, are typically 10% too strong. So this is nice that the model here recovers the bias in EIA5 winds. And by doing this, so we get away with much smaller values for the Gender-McWilliams mixing, which then keeps our mixed layer in the tropics deeper. So I think there are a couple of nice insights here. One is we are relatively fast. Within a week, we could optimize this model. So you can just go to the beach for a week and have a nicely optimized model. But we also come up with a parameter solution or parameter range that we wouldn't have found ourselves. Typically, when I tune an ocean model, I would never touch the winds. I just assume them to be true. But here there's an objective and transparent way of tuning a model.
This parameter alpha TKE, what is that? What is that doing?
This is, yeah. There was a big argument what is actually doing this alpha. I don't know, Niels, you work with the TKE scheme. Because the default value is 30, but you can get away with much smaller values.
I have to look it up, but I think it's in the dissipation of TKE. I think it's a parameter that describes the dissipation of TKE.
It's an important thing, right? And if you change it drastically, then it's also changing drastically the everything else.
Yeah, but you get a much better solution.
Yeah.
Well, but this is the one that this
Is it physical to do this, right? Because
no, this is actually, we had some discussions with the French group. This value, this default value of 30 was set in the 90s, and nobody touched it ever since. And I think it was set, or maybe you explained this to us, right? It was set to 30 in the 90s to combat some numerical noise, which with higher resolution.
Sorry, it's the coefficient that links the viscosity of the that you use for your momentum with the diffusion that you diffuse your PKE.
that is a free parameter, basically. It says that you should not diffuse PKE.
Yeah.
And this parameter for the wind stress, that's just a fixed number which you apply for the wind stress everywhere.
Yeah, so here in this, you just multiply the EIA5 wind stress with 0.85, so we reduce this by 10%.
Because you could also do this spatially dependent. And then
yeah, so I think if you want to go further down on this, we can think about, I mean, much of the bias in EIA5 happen in the Southern Ocean, so one can be more specific on this.
But then you do more or less the same as Echo or Gecko, right?
This is much easier, and this also combines them all together. We're done within a week. We don't have to do these long adjoints.
I think they also need a week. Yes.
Right, moving on. Okay. So we can we then try to apply this to several other problems. So we have now a tool where we can optimize a solution towards a given target. We are part of this ClinTip project. It's an EU Horizon project, and the subtask is to find the most fragile AMOC states. So the idea is that the AMOC that we have in our current climate models is too stable. So it will not give us a realistic projection going forward in the future. So we want to see where the biggest changes of the AMOC is if we vary the sea surface salinity. Again, we use here our Veros ocean model, which can be run on GPUs. And we use several other simulations. And what we here simply use as a loss function is the minimal AMOC. And here you see some of the visualizations of cuts through the topology of the loss function. So this yields a rather trivial result that the freshwater forcing depends on the background diffusivity and freshwater, or the AMOC strength. So this is not super exciting. This is something we could have expected, but the goal was this is the first step. Now that we have a fully coupled version of our JAX-based Earth system model, we'll apply the same and look at freshwater forcings and atmospheric states as well.
This is ocean only, right?
This is ocean only now, yeah.
But I didn't get the beginning. Why do you say that the AMOC is too stable in that model?
I did not write the proposal, but this is part of the work package. The goal is to find the most fragile states. I'm not here to defend that particular statement. I think the argument was based on the observed or the freshwater fluxes at 30 degrees south. I think in most models, the ocean exports freshwater, whether in the real world, the Atlantic Ocean imports freshwater across 30 south. Hence the argument that it's probably too stable.
These are these Dutch guys, right?
Exactly.
They always say this, and then and also Ramsdorff is also involved, and then you are in this, then you are not in this bi-stable state of this Stommel box thing, then, but you are on the stable side, basically, if the freshwater flux is the other way around, and then you cannot, your model does not have this instability, basically, if this is wrong.
Yeah. So I'm not here to defend this particular statement, but this is a tool where you can
Take the money.
answer other questions. So this is in the beginning. So Asa Stustrup developed this Bayesian optimization tool. And the nice thing is that everything is written in Python or in JAX, so it's easy to apply these machine learning tools. She spent some time then to also allow classic Fortran-models to be tuned. Yeah, you have to deal with the different interfaces between Fortran and Python. But this works now. So what we're trying to do here is to improve the precipitation in the coupled CSM 1.2. It's one of the standard climate models that is used for the IPCC reports. We have here two objectives. So we want to combat or improve on the rainfall biases in the tropics. This is the so-called double ITCZ problem. There's too much rain south of the equator and too little rain north of the equator. We want to see if with a better parameter compensation, we can improve on this range. We can first look at the results from an atmosphere-only configuration where the model is forced with observed sea surface temperature. And these are the initial points. You see we have like 200 simulations. And then again, this is different now from a normal PPE experiment. We see that we starting from the initial points, the model improves. So it finds better values here. And this is the cloud of new points moves towards smaller and smaller biases. So the optimal point will up here with zero rainfall in the north and the south. If you compare this forced ocean model with a coupled model, this is a fully coupled model now, you see you have a very different behavior. Whereas here you have, again, the initial points. Here you now have a clear trade-off between if you want to improve the northern hemisphere rainfall, you will deteriorate the southern hemisphere rainfall. And vice versa, if you want to improve the southern rainfall, you will get a worse northern rainfall. So this coupled model has a very different behavior than the forced model. I think the first lesson here should be not to tune the forced model only. It's of course much cheaper to train only the atmosphere because you don't have to worry about internal variability and you don't have to carry the cost of the ocean. But you see the tuning gives you a very different behavior because you have these air-sea feedbacks. We can then also look at the optimal values. So here are our default values for 6 different parameters of the Zhang and McFarlane convection scheme, which is still an often used scheme. If you compare these best parameters, we see that the parameter values for the no ocean group are relatively similar to the parameters value of the North group. So the North group is then the average of the 10 best points here, where we have the best rainfall in the north. But these parameter values are very different from the South group, which are up here. So the suspicion here is that by tuning the atmosphere model, the atmosphere only model, and then using this tuned model for the coupled model, or the tuning parameters for the coupled model, we favor the rainfall in the north, or we favor a good solution and neglect these possible solutions here where we have a better distribution in the south.
In Markus, it also shows that you cannot really fit, right, the observations with that model. There's something wrong with the.
Yeah, so I think this maybe it's an obvious point. You will not get a perfect rainfall distribution just by tuning the parameters. There are some structural problems as well.
What are the problems?
I'm not a meteorologist. I mean, this is an old problem. Why is the rainfall so bad in the tropics?
Question. So if I look on the axis there, and it looks like that the atmosphere one is much worse, or maybe this is misconception, but the axis is spread. You have a -2 on the no ocean axis, and then coupling it to the ocean seems to reduce this a bit, right?
This range here, yes, this range is smaller than this range, yeah.
And it's also further to the right of this plot, right? So if the 1.2 is, so we are kind of in this with this coupled thing. All the dots are actually in this blue black cloud there, right? All the green ones. So maybe, yeah, exactly. So there you would be kind of there, yeah. But this is kind of this is strange that the atmosphere model without the ocean much worse. Or I mean, for me, it's a good thing, of course. But
well, here's we have the values here. The no ocean value is 0.9 and 0.9 millimeters per day as the bias, and the source group is. Yeah, I would think the no ocean model. The no ocean model has better rainfall distribution. The best. If you couple it, it gets slightly worse. But you have the opportunity to make the southern ocean, the southern hemisphere, much better than before. Does this make sense?
And what, yeah, but there's something missing in the model, right? Would it be better if you use higher resolution? Would it improve the bias, or because it's a claim, right? But that with higher resolution, everything gets.
So as far as I can tell, even going to highest resolution, I mean, even next gens, the biases are the same. The biases don't get better in higher resolution.
But the numbers there, they don't improve. But if you would tune the high resolution model, would it improve then?
Yeah, so I mean, this is we use the T31. So this is a 3-degree resolution version. This is obviously not what people use for the IPCC reports. To do this in the 1 degree, you probably need 50 times more resources, which we don't have. This was a proof of concept. So it's a meaningful exercise to do, and we should do this for the 1 degree. 50 times more is nothing compared to, a 5-kilometer resolution run. So here are the precipitation biases. This is the model, the default rainfall compared to GPCP. We see here the signature of the double IPCC. We have way too much rain south of the equator, and we have this part here. And the same is true for the Atlantic Ocean. We have too much rain south of the equator in the Atlantic. And if we just do an average of the points where we improve on the southern part of the rainfall, we see a very nice inversion of this pattern. Doesn't have the same magnitude, but we see there's much less rain now south of the equator. And the same is true with the Atlantic, even though the Atlantic was not part of the optimization scheme. We also have this the Southern Pacific ITCZ improved here in this part as well. So this is a nice improvement of the rainfall everywhere. But we also have improvements then in the sea surface temperature and the winds. Here I just show the sea surface temperature. This is the biases. We have a general cold bias everywhere and a warm bias around Antarctica. By fixing or improving on the tropical precipitation, we improve on the cold bias. So it's a general warming trend everywhere. The shift here in the Kuroshio path is visible here. It's a nice improvement here. And we also inverse this pattern here of a warm bias here is cooled. So I think this is very encouraging that we now find with our tool another set of parameters normally that people haven't found because they were focusing on the tuning of the AMOC-based model. And looking at the structure of the solution, I would put forward that part of our double ITCZ bias, of course, by no means all of it is due to our tuning bias, that we tune the forced atmosphere model only and then apply to the coupled system. Whereas, in fact, you should tune the coupled model to get a better result. This was about the limits what we can do with our cluster at home. Much of the new computing resources are GPUs. So now we're really excited to have now our first fully coupled Earth system model, or let's say by now it's an atmosphere and ocean coupled model in JAX. So we all know VEROS. This is the Python and JAX translation of Carsten's PyOM. We've been using this for almost 10 years now. But we finally discovered a couple of groups that start to translate atmosphere models into JAX as well. And we teamed up here with Duncan Watson's group in UCSD, who translated the speedy physics. It's a relatively simple physics in the first step, and added this to the T31 Dinosaur core. Dinosaur is the core that Google used for the neural GCM. This is the current state. By the end of the summer, we should have a T85 resolution for the die core, and the icon physics is currently being translated. So we should be ready by the end of the summer with icon physics, and then we have a full 1 degree coupled model. So we use the same exercise that we did before. We try to improve the precipitation biases. Here I'll show just the SST for a change. This is the fully coupled model. And we see we have massive SST biases in the default values. And here are 2 points of our improved settings. So rather than having these massive warm biases, we have much weaker warm biases here.
Massive cold bias. Instead of massive warm bias, you have massive cold bias. Yeah. At least, it looks like it.
Yeah, but here you have values of 10 degrees, whereas if you talk about 2 or 3 degrees. So this here is a much superior solution, almost by design, because we make it.
You make it optimal testing.
Make it optimal. Actually, there's one point I should mention. We checked the top of the atmosphere radiation balance. The default is minus 0.1 watts per square meter, and the new is plus 0.17 watts per square meter. So we don't destroy any radiative balances by optimizing this here.
But what are you optimizing? This precipitation bias?
It's the same. Yeah, we do the same optimization that we did for the CCSM.
Only the precipitation bias is optimized.
The nice thing is, since precipitation controls, it's the main energy source for the atmosphere. So it controls the winds and as well as the SST. And just to show it, make the point about the winds. This is the mean zonal wind stress. The climatology is in the black line. So we have our trade winds here around the equator and the westerlies, the mid-latitudes. The default has much too strong winds in the mid-latitudes. And by fixing the rain or improving on the rain, we see that our 2 points that we have here have much improved wind stress.
Changed wind stress. Do you have a measure of the other ocean properties like the ACC transport or the overturning in the Atlantic?
No, because these are, they don't change much because it's just 40-year simulations. So,
but they don't collapse.
No, they don't collapse. No.
But this should be checked, right?
Thank you. Yeah.
Maybe you do this later.
No, we have checked it, but this wasn't the goal here right now to look at all aspects of the ocean, especially since we only have 40 years.
Yeah, but if the ocean gets worse and you improve your precipitation bias, that's also not really a success, right?
Yeah, but then we go to the ocean as the next step and see what is wrong with the ocean.
Yeah, but you want to sell us the success, so I don't buy it.
Shut him down. We're already way over the. You made your point. We have looked at the ocean, and this is the next step. But with 40 years, there's less incentive. All right. So this is now we can use this, run this coupled model now on the GPUs that we have on Lumi. So we can then use 1 degree solutions and repeat this for the full 1 degree model. But this is only one way to optimize models. There has been a lot of talk about auto-differentiability, so that you compute the gradients or the variables with various parameters during the integration. With JAX, you get this for free. So once you have a model that's written in JAX and it's auto-differentiable, you can compute all the gradients. The question, of course, is what do you do with the gradients? How do you apply to them? How do you get better solutions out of them? And we haven't started working on this in Copenhagen, but Duncan Watson's groups, Rebecca Ginny, found a way to use auto-differentiability to improve on the rainfall. So our next step will be to use this coupled model and to apply the auto-differentiability tools that Rebecca developed, and then compare our results, whether our Bayesian optimization and the auto-diff methods get to the same results. And then we can also compare the computing resources needed for these various tools. All right, so this was part one, where we try to improve the models that we currently have. Of course, you cannot, even with these models, even on GPUs, it's hard to get more than 100 or 200 years per day. So if you have like long paleo integrations or paleo problems, you still may want to look for other solutions, other methods. And then we started looking at emulators. So can we build a very cheap emulator based on the paleo observations that we have? Our first step is building an emulator for the overturning circulation in CCSM. Starting point is 30,000 years of fully coupled CCSM simulations during the last glacial maximum. There are these Dansker-Oeschger oscillations, so we have spontaneous collapses and restarts of the overturning circulation. Basically, the North Atlantic freezes over and then the overturning collapses, heat builds up, and then with the massive polynya, the overturning restarts again. And we see this played out here over the 30,000 years. We have no AMOC, then it's a sudden start on again. Then there's a small cooling, then the sudden collapse again. So we have this, I think we have about 20 or 30 of these events in this 30,000 year record. Here's a long warm period, for example, when it collapses. And after some time, then it's stable, it comes back up again. So this happens in the real world as well. And we have now the CCSM, a nice tool where we can try to understand what is going on there. But we will use now these 30,000 years to build an emulator. So we ask the question, can we build a very small set of partial differential equations or stochastic differential equations based on this set here? So this goes maybe back to some of the early ideas from Stommel, where we say, well, can we reduce the whole complex ocean circulation just into a couple of equations, but rather coming up with this on our own? We use methods to learn these equations. So the first is we do a parsimony analysis. So we use neural network-based predictions. We have a 50-year window where we try to do, we have a 50-year window here, and then try to predict the overturning 30 years ahead of time. This is our neural network-based set. And then we can ask the questions, which of the variables that we have are necessary to predict the overturning. Many of them are not. For example, wind stress in the Southern Ocean is not relevant for this system here at all. And what we came down to is to say, we can reasonably well predict the system with only freshwater fluxes in the surface between 50 north and 70 north, and between the density in 200 meter depth, also between 50 north and 70 north. With these two variables, we can train a neural network and make predictions. We see here the green line is the CCSM, and the red, the orange, and the blue are two different predictive models based on two different neural network architectures. So this works quite well, and we only need two variables. The next step is then a symbolic regression. So symbolic regression, this is a tool where you have a bag of functions and a bag of operators, like functions would be sines or exponentials, and operators would be pluses, minuses, or multiplications. And this gives you then the most likely functional form for the AMOC. This will help us to make our results interpretable. This interpretability is still something we're struggling with. I mean, this looks like a nice formula, but it's to me, it's not very interpretable. So this is something we have to think about a bit more, how to get interpretability out of this.
But what is A or B? Is this kind of an easy?
Those are just some values. I don't know, like 10 square root minus B times.
And what is the variable then here? Is this?
This is the freshwater flux at the surface. And this is the density in 200 meter depth. Yeah, one can meditate.
One. B,
yeah.
D minus 1. Density like 1025 minus 1. So that is what's coming.
Oh, it's probably.
Or it's,
No. It's a 1.0. Yeah, this is in CGS units. Like it's 1 gram per cubic centimeter.
okay.
Yeah.
Okay.
No, again, so I'm not saying this is.
Does this simple equation makes this very chaotic time series? Is it such a nonlinear thing that it can produce these as Danskad-Oeschger events?
Yeah, so if you provide the freshwater forcing and the density, then it predicts the AMOC, and this is now here the AMOC that you see.
Okay, but you have no model for the freshwater flux.
Yeah, so this comes in the next step now. So this is a relatively simple problem. I mean, neural networks will do this for you. It's very nice. I struggle with the interpretability. This is something we have to think about.
But for a model, you would also need to predict the freshwater flux and the potential density.
Didn't you promise me to take away this thing from me? So that's the next step. So the first step is we want to learn how to use neural networks to find formulas like this. And the next step is then to couple them together, and then we would have a model.
Then the test is if this model is now predicting the blue time series.
Yeah.
And does it?
Yes. I mean, otherwise I wouldn't be standing here.
Okay, then next.
Okay, so we do what I just said. We do this for, you just saw this now for the AMOC. So we have a neural network that learns the AMOC as a function of freshwater and density. And then we can do the same thing for the freshwater fluxes that learns freshwater fluxes based on the AMOC and the density. And density is then based on freshwater and AMOC. You can learn these SDEs. And then we add some noise to account for NAO, fresh and just random fluctuations in weather. And this is the AMOC time series we get with this fully coupled model. So there's no more data or outside information going in. It's all captured here. And this here is the structure of our noise. The noise is the low pass, high pass filtered time series of the freshwater. This is a fully coupled system, and this is the behavior of this fully coupled system. So you get these sudden collapses and the increases of the AMOC with the system here. This is fully learned. There have been over the last several decades other attempts to do this. They're based on coupled stochastic differential equations. One of them is here based on Fitzhugh-Nagumo, where we have these two coupled SDEs. And this is done here by Guido Vettoretti. And we see here the AMOC as a result of these coupled, two coupled SDEs. They didn't learn, but they're made up based on human intuition. And one of the key differences we see here is the spectrum. So if you look at the spectrum of our learned time series, we see this here in red. It's pretty much identical to the spectrum of CCSM. But if you look at the Fitzhugh-Nagumo time series, you have much less energy in most of the region. You could say you could just add more noise to the system, but then you lose the distinct pattern of interstadials and stadials, and you just have a random noisy time series. Whereas here we have the right high-level noise variation, but we keep our distinct sets between stadials and interstadials.
Yeah, but you could also say it's an unfair comparison because you have the optimal solution and they just guessed. They cannot have the optimal one. You are always better with neural networks. The learning.
Well, this is the goal. That's why we're doing this, because we want to have a better model than this one here. This here, I would not trust to use it as an emulator to make any science going forward. But if you learn this, you will have a better representation of the system.
Optimal, it's obvious. Kind of trivial because you are optimizing.
It is not trivial at all to create these three SDEs and then couple them and have a stable system. There are numerous tools. So I just mentioned that we use neural network-based predictions, but you have numerous tools to do this. You have a polynomial regression. You have Cindy. It's another tool to learn PDEs. You have neural operators. It takes quite a while to find out which of these tools work and to make this a stable coupled system. This is non-trivial to make this stable. I mean, to learn these three.
No, but this may be an effort to do this, but it's a trivial statement to say that yours is better than the other one because you have the optimal one.
Yeah, but I have to show that it's better. I don't think it's obvious at all.
then something would be wrong, right? If it wouldn't be better than some arbitrary choice.
So it could be that Guido is just a genius and kind of, you know, I mean, this looks nice.
He hit just the right spot, yeah, then by accident, yeah.
Are these functions complicated? Is this FHG? I mean, you because on the last slide you
so this is a neural network. This is not, you cannot write this
function. So okay.
You can also, we did this here with polynomial regression. You can use polynomial regression. Then you also get something that looks very similar.
So you're giving up this interpretability at this point.
Giving up is too much. I think I would like to continue working on this, but here we're not talking about interpretability anymore. Because we did this with polynomial regression and you have 20 different terms. You remove some of them and nothing works. So, yeah. Yes. Okay, so why do we do this? So one of the central questions is if you look at these so-called Dansker-Oeschger cycles or events, there are two basic hypotheses. One is they are forced by stochastic forcing. So you have noise in the system, like a series of strong winters or El Niños that kick the system into a new state, or it's an internal oscillation. So you have what I just described, warm water being advected, melting the sea ice, and then it's a slow cooling and freezing over the sea ice, collapsing the AMOC. But we have now a tool where we can distinguish between these deterministic processes and between stochastic processes. Because we can vary the level of noise or look at the impact of noise. And what we did here is we compared the evolution of the system in a deterministic setting. So we removed the noise altogether. Oops. This term here. Or we keep the noise as it is. And then see if we can look at the transitions. So here's one particular part. We have now more than 30,000 500-year windows. And for every one of these 500-year windows, we can make pictures like this, where we say we have the 50-year window for the initial states. And then can we predict this transition here? Here's a transition in the system. And the deterministic solution would here, in this case, not predict any solution, any transition at all. It would just stay in the AMOC off state all the time. If you do lose noise, these are our Monte Carlo rollouts, you see that several of these systems actually give you a transition. So here you would need noise to get a transition from the off state into the on state. And we can quantify, because we have these 30,000-year windows, how often the system needs noise to predict a transition and how often the deterministic system would also transition as well. We can compare this here. And here you see the deterministic transition almost never gives you a transition from off to on, whereas you have at least a 30% hit rate with a stochastic transition. So you need this noise to get from the off state to the on state, whereas you don't need any noise to get from the on state to the off state. That means there is some predictability in predicting the off state, which, I don't know what I would call this hope, but for our question of future AMOC states, I mean, can the AMOC collapse in the future? This provides some hope that there's some predictability because it's not completely dependent on noise. Even though noise is important, there is a deterministic component to the collapse, whereas there's none for the switch from off to on. Okay, this is an emulator. You can have doubts. And it turns out that Guido Vettoretti at the same time tried to answer the question, can we get Dansker-Oeschger events as a result of volcanic eruptions? So here again, you have a 5,000-year element or time series of one of these integrations. And we don't have to look too much into the volcanoes, but the baseline is how many of the transitions from off to on or on to off are done stochastic. So they are done without any volcanic forcing. So he does an ensemble of several hundred members every time here at this point. So now we look just at the blue ensemble here. So, and every ensemble has the SST perturbed by 10 to the minus 12 degrees Celsius across the globe. And these minor perturbations can lead to radically different outcomes. If you do this here, here, and here, you see the closer you are to a transition, the more likely it becomes that the transitions are caused by noise. But most of the transitions happen deterministically, whereas as we saw before with our emulator, you also see that here we have a lot of noise-induced transitions. 60% of the transitions are noise-induced, whereas much of them are noise-induced when you go from on to off. So again, this is suppose the result from the emulator that going from off to on, you need noise, whereas going from on to off, you can do this deterministically. Of course, these simulations took a year to do, and they ended up costing 200,000 euros, whereas the emulator is obviously much less expensive. But the reason to build, or the reason why we were able to build this emulator is because we had this 30,000 years of nicely resolved and synchronous model output. The real question, of course, is can we build these emulators just looking at data alone? We have these ISCO records. So one could argue with this emulator, the basic thing we learned here is how to use emulators, how to build emulators, and that we can do meaningful science with it. But as Guido has shown, if you have enough computing resources, you can still do these Danske-Oeschger simulations with a regular CCS, with a regular climate model. This brings me to the last point. We want to apply these emulator techniques to even longer time series where we will not be able to run them or explore them with our climate models. So one big question is what causes glacial cycles and what causes the mid-Pleistocene transition. If you look at the ice core records, in the bubbles you trap CO2, and the isotope ratio in the ice gives you some information about the volume of the ice sheets and the temperature. We see that we have these glacial cycles here. Let's look at temperature in Antarctica. Every 100,000 years, so this is 600,000 years, we have a warm period, and we have a long ice age, and human civilization developed here in the last 20,000 years. And we see this about every 100,000 years, and it's highly correlated with CO2 and with sea level. What the sea level is the volume, the inverted volume of the ice sheets. Sea level is 100 meters lower. That means all this water is building up in ice sheets, and we have an ice age. If you go further back in time, we don't have ice cores that are older than 1 million years. We have to use sediment cores. They are not as well resolved, but you can go back further in time. This here is the famous Lisecki and Remo stack. I think they added 20 different sediment cores. And this again gives us some idea about the volume of ice sheets. We have almost no stable ice sheets before the Pliocene. The Pliocene started 2.5 or 2.8 million years ago when there was the first inception of a year-round ice sheet. And then as you see, Earth has been colder, and in general, there has been a build-up of ice sheets throughout time. It is assumed that this is because of a slow drop of CO2. It's hard to know because we don't have CO2 records over these time periods. And one big thing that happened about 1 million years ago is that we switched from 40,000 year cycles here to 100,000 year cycles. This is a big mystery in paleoclimate. 40,000 years is nicely aligned with the Milankovitch cycle that changes in Earth's orbit. 100,000 years is not. So where does the 100,000 years come from? This is really a fundamental question. That also means we still don't understand what causes ice ages. If you look very closely here at the glacial inception, and the glacial collapse of the ice sheets, or the warming, you see the temperature is leading CO2. So that's one of the big stories that we tell the media or the public, is that because CO2 increases, the temperature rises, whereas in all of the recorded paths, it has been the other way around. First, the temperature increases, and then CO2 increases. So I think this is an important question to answer. And climate models haven't been able to reproduce this glacial at the end of the declassiation. So there's something that we don't understand. And the goal is now to build an emulator that can use these records, that we learn something about the fundamental balances here. The two leading hypotheses related to the switch from 40,000 years to 100,000 years is, one is that the carbon cycle has become more active, so CO2 plays a bigger role. And the second hypothesis, ice sheets have become more stable, so you can make them bigger than before, but don't know. So in the first step, so this is now a time range where we'll not be able to use Earth system models anymore. And the first step was what you saw before. We try to learn to build emulators for these systems. And in the beginning, we have guidance from CCSM. The nice thing is the data is highly resolved and it's perfectly synchronous. We were very encouraged with Schiffan's results for the Dansker-Oeschger event. So we immediately tried to do this for data and nothing works. So this was very disappointing. So we went back and said, well, let's first try to do this on synthetic data. So we want to build an emulator that emulates another, basically, emulator. What we use here is the Salzmann and Marsh model for the ice ages. So this is a set of three SDEs. X is the global ice volume, Y is the CO2 concentration, R is the insulation, and Z is the deep ocean temperature. So Salzmann and Marsh claimed, I think quite believably, that these three equations are enough to reproduce the observed behavior. This is what you see here. So Florian rebuilt their model, and this is the insulation. This is 4 million years of insulation. And we have here then the ice volume, CO2, and temperature. And you see you have fluctuations. Sometimes you have 40 years, 1,000-year cycles. Sometimes you have 100,000-year cycles. So this model is able to capture the different frequencies we have in the observations. And our goal will be now the first step to learn this thing.
But Markus, this equation from Salzmann and Marsh, this is not a stochastic equation, right? It's a forced.
Sorry, it's it's just a set of three.
I don't need noise.
No.
Where does this R come from, this equation?
This is the insulation. Oh, so this insulation is 65 north. This is from Peter Heubers.
This orbital parameter.
Sorry, this, yeah.
But it's kind of contradicting, right? What you've first said, that you need noise to make these transitions, and everybody talks about stochastic differential equations, and they can do this without noise.
Wait, but this is a different time frame. So here we talk about the Dansker-Oeschger events. This is during the last glacial maximum. Every couple of 100 years we have an on and off. Whereas we're talking about ice ages, right?
Yeah, these lines, they all look the same.
So before we talked about this little period here, and we see the Dansker-Oeschger events in here. Now we're talking about glacial interglacial cycles. So it's a much longer time scale with much larger amplitudes. You can look at the Dansker-Oeschger oscillators as the little sisters of the big glacial cycles. Okay, first we try to learn the Marsh model, Salzmann and Marsh model. And there are a couple of things that we learned, or especially Florian Zicker, that's Florian's master thesis. In principle, first we try to use the methods introduced by Schiffan, but two things are really necessary to make this work. One is we have to use Sobolev loss for the objective function. So before this, in the objective function, we just use the difference between the model and the CCSM results. So this would be just a regular RMSE. And with the Sobolev loss, we also learn or also make sure that the gradients or the Jacobians and the Hessians are matched as well. It means that the acceleration with which the warming and the cooling happens and the speed with which it happens. So this was an important step to make the loss function a bit more complicated and account for different variations. And we also don't predict just for the learning, we don't just predict 20 years ahead in one time step. we actually predict 20,000 years rollouts. So we predict the whole set of the time series. Once you do this, then you're able to actually rebuild or reproduce the Marsh, Salzman Marsh model. Maybe the figure doesn't come out too well. So the red line here is, the solid line is the Salzman Marsh model, and the broken line is a realization of the learned model. Maybe it's easier to see here in the spectrum that Salzman and Marsh is here the blue spectrum. We have here the 100,000 years and the 40,000 year peaks. And our emulator now has similar peaks and similar levels of noise. So this is exciting.
Yes, right. You talk about noise now.
Well, so 40,000 years is an orbital signal, is astronomical forcing. This here, everything else I would call noise.
But it's not noise driven, this model. Also, the emulator is not noise driven, right?
Okay, I call this, higher frequency variability. How's that? Yep.
Why is it that your emulator doesn't get this really high frequencies?
I'm sorry?
Your emulator, it looks like that your emulator is not really getting this really high frequencies, right? There's a clear mismatch between the blue and the orange.
Yes, because there we have to add noise in the learning procedure. So I only highlighted two of these things that we have to do on top of what Shifan has been doing. To make this robust learning procedure, you do add noise in the learning process. If you don't do this, you will not be able to reproduce these time series and they will collapse. So there was a lot of learning done here by, there's a whole literature of how to build emulators of dynamical systems. So these are the two of the key steps, but again, adding noise to the system helps as well to make it more robust. Okay, so this was just the first step, and we are still don't have any interpretability. So the next step will be, can we, based on this time series that we learned on this dynamical system, can we back out this formula? Because here, this formula, we know how it has to look like. And the thing is, can we back out this formula based on our dynamical system, or to inverse it essentially? And the other one is, can we use these tools for the observations? The observations are gappy. They're not synchronous in time. We have an ice core in Greenland and an ice core in Antarctica. It's hard to synchronize them. There are methods, but this is a big challenge. And it's not obvious how robust these methods are if you have asynchronous time series. Yeah, sorry, I was a bit over time, but so for the first part, I hope I convinced you with this Bayesian optimization, we can discover unexpected parameter settings, the unexpected and superior. And I also hope I convinced you not to tune AMOCs, to compute AGCMs alone. It's really very helpful to tune the fully coupled model. It gives you much superior results. Then we're excited here to introduce JASM, our JAX Earth system model. It's also a very nice tool for students and for prototyping because it runs on GPUs. It's much faster to use. And especially for students, there's not a single line of Fortran in there. It's all based on Python. I'm excited about this auto-differentiability part. I'm not sure yet whether it will work. It's a much more challenging problem than simple Bayesian optimization. But within the next half a year, we should know where we stand. Then moving on to deep time. I think we're able to build emulators now of dynamical systems. We do have long time records or observations in the ice cores and sediment cores. And this may allow for equation discovery. Again, this is now an open question. And that's something that will keep us busy for the next year to turn this into an interpretable set. Yeah, thank you.